Hello, everybody. Welcome to lesson 5.2. Today, we're going to talk about defining the integral. So last time we talked about using Riemann sums to estimate the area underneath the curve. And today we're going to talk about how we can use that to define the basic idea of what an integral is. So let's get cooking, defining integrals. So last time we talked about Riemann sums, right? And what we noticed about Riemann sums is we could take this delta x, which was the width of each one of the rectangles, and it was defined by the width of the integral divided by n. So the width of each rectangle was the width of the integral divided by n, where n was the number of rectangles that we had. So for example, in the one that we did in the video, the width of this interval was 2, and we created 4 integrals. So our delta x was 1/2, because it was a width of 4 divided into, or a width of 2 divided into 4 subintervals, because that was the number of rectangles we used. So if we can use this notation down here to generally describe the sum of all of those. So this little e thing right here, this is summation notation. What it means is take the value of the function at one of the endpoints or the midpoint, multiply it by the width of the rectangle, and add up all of these from the first rectangle up to the nth rectangle, where n is the number of rectangles that we want to use. So the idea is, what happens to the width as we add more and more rectangles? Well, the width is going to get smaller and smaller, but what's going to happen if we add more and more rectangles? Well, as we add more and more rectangles, it's going to get closer and closer to an actual evaluation of the area. So right here, if I were to add in a whole bunch of little rectangles right here underneath this curve, so let's say that this is the x-axis down here. If I were to add in a whole bunch of little rectangles here, as I add in more and more rectangles, my answer is going to get more and more accurate. So in general, if I could take this expression right here and write a limit as n approaches infinity, then it should give me the actual area underneath the curve. So that's exactly what we're going to do. We're going to find the limit of this as n equals infinity. If you notice here, this is now actually equal to the area. So right here, this was an approximation because we were using a finite number of integrals, or of rectangles. But if we find this limit, then we can find the limit as I approach an infinite number of rectangles, which means the widths will be infinitely small and it will give me the exact area underneath the curve. So to do this, we're going to use the integral. So up here, this is the definition of the integral. Basically, this notation right here is the integral from a to b of f of x dx. Right here, this dx tells us what we're integrating with respect to. So I'm going to show you one example right here. You technically wouldn't know how to do this yet without defining the fundamental theorem of calculus. But the idea behind an integral is that it is an antiderivative. So an antiderivative means I'm going to look at this and I'm going to say, well, what could x squared plus 1 be the derivative of? And the idea here is, if this is x squared plus 1, this is the integral of 1/3 x cubed plus x. And then technically there should also be a plus c, because if I add in any constant, the derivative of any constant will be 0. So I wouldn't actually see it inside the integral here. But what's going to happen when I do this is, if I'm finding this integral from 0 to 2, then I'm going to take this function and I'm going to plug in 2, and I'm going to plug in 0, and then I'm going to subtract the two functions. So when I plug in 2, this would be 8/3 plus 2, and then plus c. I'm going to include the c for now so that you can see what happens when I do include the c. Minus, if I plug in 0 for each of these, this would be 0. So then this would just be minus 0 plus c. So the reason the c is not important with definite integrals, so remember what I just said there, it's not important with definite integrals, is when I subtract these two things right here, c minus c is 0, so I don't need to include it when I'm taking definite integrals. So then if I add these two things together, this is 6/3, so this area would be 14/3. So what this means is, last time we found some estimates for this area underneath the curve. This 14/3, this is the exact area underneath the curve between this function and the x-axis. All right, so we're going to use this in a second to apply some properties of definite integrals. So these are properties of definite integrals. You will want to pause the video and write these down. I'm not going to stop right here. In class, if you have any questions about what any of these mean, you can ask. But I'm going to keep going because you can pause the video and write these down. And we're going to use a few of them to take, or to show how a few of these properties work. All right, so we just found out the integral from 0 to 2 of x squared plus 1 dx was 14/3. So we're going to take that and look at these three things. So this first one, if I notice, I switch the bounds, which means I'm going to change the sign of the integral. So then this is going to be negative 14/3. All right, that's one of the properties. If I switch the bounds, I switch the sign of the solution to the integral. Right here, I notice this is just 10 times this expression, which means that the solution is going to be 10 times this value. So this would be 140 over 3. This is another one of the properties. So I multiply by a constant. I can just multiply the value of the integral by the constant. And then this third one, I notice this is the same integral. I've just changed the variable that I'm integrating with respect to. So nothing's going to change. I've just changed this to a t instead of an x. So if this is the integral of x squared plus 1 dx, then the integral of t squared plus 1 dt would also be 14/3. So that is the end of the video for today. I hope you guys took some good notes. And if you have any questions, I spelled definite wrong. Definite. But if you have any questions, I hope you bring them to class. And I hope you have a fantastic day. I will see you in class. And I hope to, well, you'll hear from me in the next video. Have a great day.